Today we will be going over theories as social constructs, a way of trying to come to a consensus as to what scientific understanding is. The reading for this lecture is Directed Deeks, A Contextual Approach to Scientific Understanding. If you haven't read this, please pause, go read it, and come back. The lecture has three primary topics. First, we'll return to the idea of understanding, linked to earlier lectures at the beginning of class relating understanding and knowledge to statistical learning. Then we'll go over a contextualized approach to scientific understanding as proposed in the reading. And then we'll go over the issue of intelligibility and scientific understanding. So let's start by returning to the concept of understanding as relayed at the beginning of class. If you recall, we opened talking about the concept of empirical risk minimization, and that the goal of data science and statistical learning is to develop a hypothesis about relations in your data that's the best reflection of the true underlying associations, which we'll call the true hypothesis. So you're going to use statistical tools to learn the best model of your data and try to make that as close to the true model as possible. And one key feature we've gone over repeatedly in the class is the idea of generalization, whereby given a fixed training data set, find the model that best predicts future unseen data as close to the best possible model, which we'll call H-true. So the goal of everything we've gone over when we talked about fitting models and cross-validation is to essentially find the best minimum expected risk of your data. Now you recall that when we define risk here, it's a loss function. So it's the difference between your hypothesis given x, or the model you have of y given x, versus the true observed y itself. So this is often the square difference, or it's an accuracy term or an error term when you're doing classification. But the overall goal of statistical learning is to minimize this empirical risk across both the training and the test set. So we've got the test set here in blue, which reflects the kind of holdout validation, and the training set in magenta here, which reflects the distribution of data you use to learn your model. And this is the fundamental premise of data science and statistics. Now, using this concept of empirical risk minimization, at the beginning of class, we went over trying to take a statistical learning perspective as to what is actually knowable from your data. And we said that a signal y carries information that x is f if y equals f of x is learnable. So in other words, you can extract the information about y that's embedded in x by learning the best function possible from the data. And if it's learnable, then you can carry out that information about the nature of x and its relationship to y. Now this is a phenomenological description of learning and knowledge. It just says if you can learn it, then you have information about the relationship. Here f of x conveys the mutual information between x and y. Determining that x is f, that x is in some particular state f, or relates to some particular concept f, is an inference goal, not a learning goal. And so we have to dig deeper into the data beyond just learning a model in order to understand what x is saying about the underlying construct you're trying to study. And in this case, knowledge is restricted to contexts where your data is IID, independent and identically distributed. And that's in both the test set and the training set. We talked about this a little bit at the beginning, so we can use this empirical risk minimization framework to differentiate information, knowledge, and understanding. And in the context of statistics and data science, you garner information about your relationships in your data when you just train a model. So when you've just trained a model on the data set, you've minimized your empirical risk based off of some fitting procedure. You've garnered information about the relationship between X and Y. When you can then generalize effectively from that learned model to a holdout test set, we say that you have some knowledge about the relationship between X and Y. So it goes beyond just fitting a single model and trying to infer structure from that model, but you can get a degree of knowledge about Y when you can predict reliably in unseen observations. And this is the dominant form of what we talked about in the knowledge section of the class. Now, in this context, we assume that your test set and your training set are IID, that the data comes from the same distribution. However, in order to build a robust, generalizable model of the world, you want to go beyond this IID assumption. And this is where we talked about measuring or detecting the phenomena of understanding. When you can learn an effective model that minimizes empirical risk from a training distribution and generalize it to a new test distribution that isn't identical to your training distribution, it can be correlated but not identical, then we said your model has some degree of understanding of the underlying processes you're trying to describe. And if you take a step back and do a meta-theoretic analysis here, you'll see that what we're describing here is a more general phenomenon as to what you can do when you have understanding. Understanding allows for you to make novel predictions in new contexts that might have invariances with the context that you learned your original model from, that you learn your original understanding from, but aren't identical to it. So we're going to focus here on this idea of understanding as being this kind of generalization to novel context. And the argument made in the paper, I think quite clearly, that was the reading for today, is that this is a fundamental goal of science. When we build theories, when we build models of phenomenon we're trying to describe, essentially what we want to do is we want to build something that we can then apply into fundamentally new contexts. We want something that's general enough and adaptable enough to really generalize outside of our original set of observations, to go beyond this IID assumption. And this is the fundamental goal of the direct and Deeks reading that we had for today. Let's think about scientific understanding in the context in which it occurs. So the reading that we went over really tries to address the question of what is scientific understanding, but from a normative and almost anthropological point of view. So the question is not what would be ideal scientific understanding, but the goal of the direct and Deeks reading is to really understand what is the process by which communities of scientists come up with their theories and come up with their understanding, and what are the mechanisms that facilitate it. So let's start by just getting some basic terms under our belt. When we're talking about understanding, an important aspect of scientific understanding is the concept of an explanation. An explanation is a mechanistic or phenomenological description for how factors or observations relate to each other. The explanation could be something as simple as a linear regression model, the specific weights that you fit on your data, that gives a clean mechanistic explanation for how a change in X relates to a specific change in Y. That's very narrow. Taking a step back, a distribution of explanations or a set of explanations can lead to understanding. And I really like this quote from Newton Smith that was in the reading about what understanding is. According to Newton Smith, understanding is some deeper theory that explains what it was about each of these apparently diverse forms of explanation that makes them explanatory. So in this definition of understanding, a theory or some other model ties together explanations and gives a deeper set of understanding or a depth of understanding about the relations that are trying to be explained by each individual explanation. And the goal of the reading today was for answering, what is this? What is this understanding? And how is it achieved? In order to understand the nature of scientific understanding, according to Direct and Deeks, we have to take a step back and think about the levels at which scientific theories exist. And they lay out 3 general levels of explanation. First, there's the macro level, which you can think of as science as a whole. This is a culture, a human culture that exists independent of individual disciplines and agrees upon some general consensus of how to understand the world. So the high level approach or field of science has common understanding around the idea of using the scientific method in order to build an intuition or understanding of the world. Within the macroscopic level, you have subcommunities, specific scientific disciplines, astronomy, chemistry, neuroscience, psychology. Each one of these are separable scientific communities. These are whole groups of people oriented around a common question. And at the micro level, you have the individual scientists themselves. Now, Direct and Deeks argue that achieving understanding is a general macroscopic level aim of science. This leaves open the possibility that scientists at different points in time in history or across different communities might have different views about precisely how understanding can be achieved. So physicists might have a different view of understanding, scientific understanding, than a chemist or a psychologist. And that's fine according to this perspective. But the overall goal of science itself is to produce understanding about the world. But because you have these differences across communities, with respect to at least understanding and intelligibility, the authors argue that the most important level for understanding this is this meso level. In particular, how specific scientific communities build standards and tools and skill sets in order to share their knowledge towards the development of some general theory. So while scientific understanding might be a macro level goal, its implementation, according to Direct and Deeks, is specific to the scientific communities, the meso level level of explanation of science. Now, it's important at this point to distinguish 2 reasons for needing scientific understanding. And there is no general consensus in the philosophy of science as to why scientific understanding is important. But these are the 2 broad ways that the philosophy of science field talks about it. First, there's the pragmatic approach, which just says that explanation and understanding are simply subjective means of meeting some human need and drive. The quote from the paper is, it's a function of our interests and pleasures. So from one perspective, people view scientific understanding as just some pragmatic ends of discovering a truth, but has no epistemological value. Now there's another camp that says that explanation and understanding are the fundamental goals of science itself. And we just kind of went over that in the last slide. And for a long time in the philosophy of science literature, these were seen as competing concepts of explanation and scientific understanding. Some people were arguing you just need it for pragmatic ends in order to implement the process of science. Other people were saying that they are the ends in and of themselves. And what's nice about the Direct and Deeks reading is that they argue that this is kind of the same thing. Understanding is an essential ingredient of the epistemic aims of science itself. And without understanding, these aims would remain out of reach. So it takes a pragmatic approach and says that the implementation or the means are the only way to achieve the ends, and therefore these are the same. which I think is kind of a powerful way of looking at the utility of explanations and understanding in science. You want to be able to effectively convey what you learn from your data and observations, because that effective explanation and communication helps build the broader goal of the community's understanding of the phenomenon you're trying to describe. So if we agree that understanding is an epistemic goal of science, let's take a look at some of the conceptions of scientific understanding in terms of how it is expressed. And in the paper, they go over 3 different models of scientific understanding that have been proposed in the literature. The first is the causal mechanical model. And this says that scientific understanding only progresses via causal theories for the world, explaining causal interactions and processes. This was proposed by Salmon in the 1980s. And in this idea, it says that you can only truly understand a process you're trying to study if you can frame it in a cause-effect kind of a framework, right? So this has intuitive appeal. If you understand causal relations, you can generalize fairly effectively outside of the narrow situations where you tested this. If you know about the Bernoulli effect, you can make an airplane wing. And so I think for a lot of science, this causal mechanical model makes sense. However, as was pointed out in the reading, this does fall apart under various under strict analysis. And the example that was brought up is the Einstein-Podolsky-Rosen model, which is a quantum physics model. And it breaks down this strict need for causality, because in the EPR model, a direct causal connection is impossible because the 2 correlated events are too far apart in space and time for a signal to connect them. So these are kind of action at a distance types models. And there is no direct cause for the correlations events. And there's actually lots of examples of correlational or association-based explanations and understanding in quantum physics in particular, but many aspects of science. And so a strict requirement for a cause-effect relation for being a model of scientific understanding kind of falls apart relatively quickly once you pull at those threads. An alternative approach is the unificationist model. And so this says that you don't necessarily need cause and effect understanding in order for it to be a scientific model. Instead, your goal is to unify across observations or unify across explanations. So here it says the scientific understanding reflects a unified picture of the world. A quote from the paper that I like from Friedman is that a world with fewer independent phenomena is, other things being equal, more comprehensible than one with more. It's a parsimony argument. The more you can unify and compress an understanding across observations and contexts, the better understanding you have of the world. Now, unification can be an effective tool for achieving the goal of scientific understanding. And seeing analogies between theories in the form of similar argument patterns is a way of extending the range of particular skills that you're needed for communicating understanding. But understanding can also be increased by internalizing 2 or more different argument patterns instead of just having one. So you can actually build an understanding not by unifying different concepts, but by contrasting them, or by showing how they run in parallel. And there's lots of examples for where the unification idea for scientific understanding kind of falls apart at the edges. And the proposed alternative, which kind of subsumes both the causal mechanical model of understanding and the unificationist model, is the contextual model, which is what's being proposed in the direct and Deeks reading. And here they say that scientific understanding is a contextual process, influenced by meso and micro level differences, and should be seen as a socially driven phenomenon. I think this is a critical point that's worth pausing on. Here they're saying that scientific understanding is a social phenomenon. that it is in the communication of ideas across individuals and the convergence of those ideas that you have a drive in scientific understanding. And this is not an optimal way or an ideal way of achieving scientific understanding. What Direct and Deeks are arguing is that this is how it happens in the process of science itself. When you watch communities of scientists work together, this is what achieves scientific understanding. And this is what constitutes scientific understanding, is this agreement across individuals. So it's at that meso level that's important. Let's take a closer look at this. Imagine you have a single scientist who comes up with an idea. Now, if this idea isn't shared, does it have really a utility? We're going to have the tree falling in the woods phenomenon here. So what do we do when we have a scientific discovery? Well, we communicate it. We write papers, we give talks, we do interviews, and we communicate it to our broader community of scientists in particular. And this communication relies on our theories and discoveries being intelligible. You can think about this as being a communication problem now. You have a signal, the single scientist on the left. You have the receivers, the other scientists on the right, and the amount of information that's carried across the channel. And the capacity of that information transmission is defined by the intelligibility of the idea. And in this way, what you do is start to contribute your idea to a broader collective understanding of how the world works. People start to converge on theories about how brain systems work, people fall for biases, etc. And in this way, the unified idea is a collective property of a community of scientists. In this way, one should be able to use this general theory to drive predictions or describe future unseen events of whatever phenomenons of interest. This community-driven idea is what gives us new predictions to test, new ideas to evaluate. And what this says is that not only is there the issue of knowledge of just general laws and theories and all the other background conditions of science that are necessary for building scientific understanding, but there's the particular skills of the individuals in communicating these ideas that's necessary for achieving this epistemological aim of science. So what this does is it introduces kind of a pragmatic element, that it's not just the structure of the ideas that's important, but how they're communicated that's critical for the notion of scientific understanding. And the quote from the paper is that a scientific theory should be intelligible. We want to be able to grasp how the predictions are generated and to develop a feeling for the consequences of the theory, or consequences that the theory has in concrete situations. Now, in order to really understand this pragmatic element of scientific communication, Direct and Deeks point out that we have to come up with criterion for intelligibility and understanding. And they propose two critical criterion that define both what understanding it is and what intelligibility is. Let's start with understanding. Direct and Deeks propose a criterion for understanding phenomenon, or CUP. And their definition is that a phenomenon P can be understood if a theory T of P exists that is intelligible and meets the usual logical, methodological, and empirical requirements. And these are the logical, methodological, empirical requirements of the scientific community. Remember, we're sitting at that mesoscale here. So just a couple of points on this. The CUP reflects a generally accepted theoretical framework that determines whether a phenomenon is understandable in principle. So it's context dependent and meso-level. Now, this doesn't mean that every theoretical framework will meet this, and there might be mechanisms of understanding that sit outside this, but in principle, the CUP just describes the general properties of theoretical frameworks that lead to understanding. Another point that is pointed out by the authors is that to provide scientific understanding, any proposed theory must conform to the usual logical, methodological, and empirical requirements of a field. That last parenthetical phrase is important, which means that there are context-specific requirements that might vary across scientific communities. This allows for variation in how understanding is achieved across fields. But there's one critical word in the criterion for understanding phenomenon that we have to dig into more, and that's intelligible. So Direct and Deeks come up with a criterion for intelligibility of theories, CIT. And here they're saying that a scientific theory T is intelligible for scientists in context C if they can recognize qualitatively characteristic consequences of T without performing exact calculations. So the idea is that a theory will be intelligible to other individuals if they can understand or recognize characteristics of the system you're trying to describe without having to dig into the actual equations. So a couple of expansion points here. This criterion for intelligibility of theories captures the pragmatic and contextual nature of intelligibility, and thus is kind of a key to achieving the criterion for understanding. In addition, it allows for the possibility of a scientific theory to be considered unintelligible by one community, but intelligible by another. Anytime you've tried to open up a journal from another field and it seems unintelligible, well, this is why. The criterion for intelligibility of theories says that they're only going to be intelligible within the context of the community that's doing the communication. And it might be intelligible for them because they have this history and community agreement as to what terms they're using and assumptions they have. Now, the example that's one of the examples that's used in the reading that I quite like is the example of Boyle's law. Now, Boyle's law is just describing the relationship between pressure, volume, and heat. And by definition, Boyle's law says that pressure is inversely proportional to volume. For the same amount of matter, or gas, in a liquid, as volume decreases, pressure increases. And the example that's used in the text talks about Boltzmann's explanation of this phenomenon. And Boltzmann described this phenomenon by imagining molecules in a container. These molecules are like balls bouncing around the walls of the container. If you have the same energy, the balls are all moving around at a common speed, and so they will hit the walls of the container at a certain frequency. Now, if you maintain the same temperature, but just decrease the overall volume, intuitively you can see how you're going to get more interactions or collisions between the molecules themselves and the molecules in the wall, which will generate heat and increase pressure. What's beautiful about this example, this very just simple intuitive example, is that it provides a qualitative understanding of relations between pressure, volume, and temperature without actually needing to perform a calculation. Every introduction to chemistry class or a physics class explains Boyle's law in this intuitive conceptual manner by imagining these balls bouncing around containers. You don't need to dig into the math, you don't need to know derivatives and rates. All you need to do is imagine balls bouncing around in a container. And in this way, this is a very intelligible way of communicating the idea of Boyle's law. There were lots of other examples in the text. I think this is one of the easiest to intuit. But it makes a very important point. You can communicate your concepts and ideas in colloquial or analogical terms, and that's important. Because the easier it is for people to understand what you're saying, the easier it is for them to accept and work with those ideas. And that's important because a lot of what we're doing in science now drives down through statistical equations. We've spent a good chunk of this class working on different forms of statistical models and how to interpret from them. But it is crucial to be able to translate what you're seeing in your statistics into colloquial prose that can be intelligibly communicated to your colleagues. Now, it doesn't have to go as far as being accessible to a broader public. You can use jargon, you can rely on assumptions, but you still want to explain your statistical outcomes and your results in an intuitive, intelligible manner. And that means you're going to have to rely on what the authors called conceptual toolkits. And what they mean by this is that the CIT and CUP define requirements of the skills and tools needed for achieving scientific understanding. Now, what are these skills and tools? Well, there's a variety of them. You can think about visualization standards. We went over this when we talked about scientific visualization. There are community standards for what types of plots you use or ways that you visualize data. Those, as they become community standards, are sets of tools that make for an effective, intelligible communication of ideas. There's consensus of definitions of terms, common analogies that are used. For example, there's the overused computer metaphor of the brain. This helps people understand ideas in an intuitive way. Common inference standards. Do you use a common p-value criterion? Do you rely on Bayes factors? Communicating mediums. So for example, what journals are you submitting to? Are there conferences that you go to? What are the means by which you meet and communicate your ideas? These are all field dependent. Vetting procedures, so for example, how peer review is done. Some fields use open peer review, some fields use completely double-blind peer review, some fields just use one-dimensional peer review, which means that only the authors are blind as to who the reviewers are. These are all standards that set up a set of skills and tools that are used for communicating ideas. And these are pragmatic, principled tools that are effective for communication. And you want to think clearly and carefully about the community you're trying to talk to and what these shared skills and tools are. The classic example that was brought up in the text, and I really quite like, is the concept of a Feynman diagram. And this is your kind of general classic example of a Feynman diagram. And Feynman diagrams are ways of kind of compressing interactions of quanta in physics across space and time at a level that space and time doesn't quite work in the same way as our physical world. Right? So these are not necessarily intelligible to a lay audience. You're not going to understand how electrons are going in and out of phase intuitively by looking at this diagram, but anyone in physics or anyone trained in particle or quantum physics will be able to look at these diagrams and know exactly what's going on. They communicate effectively interactions of quantum matter or particle matter in a way that people in the field can understand. And so if you want to effectively communicate your ideas, you want to rely on these toolkits. And we went over a bunch of these toolkits in our class. How you can visualize your results, how you summarize your data, how you can tie across different statistical tests to come up with a unifying, holistic picture of your relationships, how you can effectively communicate these ideas, how do you write effectively for this. And the reason this comes after we talk about how to write a paper is that you want to know why it is that we paid attention in a data science class to how to write a paper. Because everything you do with your statistical analysis of your data and your data cleansing, your data summaries, is meant for this sole purpose. Communicate to others. Use your work as a means of nudging the community towards a new or revised model of how the world works. That's what we're doing. So as your take-home message, I hope you've seen that scientific understanding is a contextual process. It relies on a community of researchers coming together to build generalizable theories. In this way, you can't think of scientific understanding as being the process of a lone researcher. Only the community itself builds this common model that exists in this kind of meta space of our shared understanding of the world. And what this means pragmatically is that communication efficiency, which we called intelligibility, is critical in this collective process. So rather than seeing intelligibility as being a a simple, small, pragmatic process, Direct and Deeks make a very powerful case that intelligibility is the means for achieving scientific understanding. And without it, we can't collectively come to an understanding of the world.